Hello, advanced math students who are interested in the extra credit project for our polynomials unit. I wanted to give a quick overview of the notes that we did in class today, just so you could see where, as we move to the next page of notes, I'm referring back to. I'll remind you that your project is specifically designing a polynomial to have a certain type of root. There are 4 different types of roots that are outlined in your document that we went through, which are irrational roots, imaginary roots, a root that is both irrational and imaginary, and then complex roots. We also talked about how those roots are always going to appear if we are going to get a polynomial with integer coefficients, which is kind of the smaller family of polynomials that we're restricting ourselves to here at an advanced math CP level of understanding of this idea of polynomials. If you are going to have any of these 4, they have to appear in either opposite or conjugate pairs so that you can get back to those integer coefficients. So what we talked about in class today at the end is that we were going to be creating corresponding factors with each type of these roots, and as you can see, all of the pink underlined, squiggle underlined here, factors are what would result from the 4 different types of roots. So I want you to know that as we move on to creating the polynomials here, we're going to take the pink underlined factors from above and we're just going to multiply them by any additional factor of your choice, okay? My particular choice, and I chose to keep it the same for all 4 different types of roots, for the irrational, for the imaginary, for the irrational and imaginary, and then for the complex, the 4 different cases that we have there. Again, I just decided to keep my other factor that gets it to a 3rd degree the same throughout. So the blue underlined polynomials that you see as a result are what you would get by using the FOIL algorithm of the distributive property. So the squiggle blue polynomials are what we're going to start using as we talk about how to verify each one of these special types of roots by using synthetic division. It's a different context than how we've used synthetic division before. So that's where we're headed right now. So if we are using the polynomials we came up with previously, and notice I've squiggle underlined these in blue so that you can refer back to the ones we just came up with there. And if you need to, go back and take a pause on the video and write those down if you need to see that multiplication out a little slower. But I wanted to show you what the work looks like for each one of these. So first off, if we're looking at irrationals, then we can look at the first row with the coefficients from the squiggle blue underlined polynomial from the previous page. And I just want you to keep in mind that we have several layers of synthetic happening here, as we have for higher degree polynomials often, and that anytime we are looking at an irrational root or imaginary root or any of the others, of course we know our root or our 0 is going up in that upper left-hand corner. So as we multiply through and add through this synthetic algorithm, I want you to keep in mind that we're keeping all of these exact, okay? So you don't see any decimals here, you only see simplified radical form in this case. So as you know, we start by pulling the 1 down, we multiply these 2, and we get the square root of 11. We add down the vertical, so we have then 3 plus radical 11. That cannot be simplified. So what we're going to do next is we're going to distribute this square root of 11 throughout this binomial here, and we get 3 radical 11 plus just 11, because the 2 radicals end up multiplying to just that whole number plus 11 there. If I add that result, which was these 2 things multiplied together here, to the coefficient above it, then the 11s end up canceling out, and I get just 3 radical 11. If I multiply again that back by my divisor or by my root here, 3 times radical 11 times another radical 11 gives me a positive 33. And add that to the constant that's above it, And we get yes, looks like that square root of 11 root checks out. Remember, if square root of 11 works, then negative square root of 11 works. So we're going to do that same synthetic process. Pull down the 1 to start, multiply, add. Notice what happens there with the radicals is that they disappear. Multiply, and then add. And we've got 3 times radical 11, a negative, plus 3 radical 11 that was positive above there left over from before. And so we get that that one checks out. Now look at what we have left. Hopefully you can see we have x plus 3 left, or if we fed negative 3 through, we would see that all 3 of those roots check out synthetically. The next type of root we want to talk about is if we are using synthetic to check our imaginary roots here. And so we have, to begin with, the examples that I came up with on the previous page again. In this case, we decided we were going to prove that 6i and negative 6i were a pair, opposite pair of imaginary roots. So we start with the polynomial that results, that's the squiggle blue one from the previous page. And as we pull the 1 down, we multiply, we get 6i. We add to the coefficient above it. 3 and 6i are completely unlike terms, so I can't simplify that, so we'll leave that as a 2-term complex number. And then I still have to multiply these 2 things right here. So I'm going to think about distributing, and notice I have the products written off to the side here, as I have before with long division. So I have 6i written as a distribution through 3 plus 6i as 18i, and then plus 36i squared. Now don't forget that anytime we have I squared, we got to put in a negative 1 there. So we get negative 36 plus 18i, and that's going to be rewritten as what we're going to add in the next spot to the 36 coefficient that was there to begin with. Notice what happens to those 36's. They disappear. So then we just have an imaginary piece of 18i below, and then we're going to multiply again by the 6i that is my root. 6i times 18i is 108i squared. Substituting that I squared, we get negative 108, which added to the constant above it does check out as, yes, this truly is a root. So this is kind of cool. Now, if 6i is a root, remember, then the opposite root, negative 6i, also is, if we're going to keep the idea of only integer coefficients in our polynomial. So let's pull that 1 down, multiply through, add. Look what happens to those 6i's. They're already designed to kind of disappear on us. So we've got the negative 6i, that's the product here, added to the leftover value from the previous layer of synthetic, and we just get 3. Multiply the negative 6i times the 3, and we just get negative 18i, and you can see that's designed also to nicely cancel out for us. Feed that last root through of negative 3, and yes, all 3 check out. Okay, let's take a look at the next type. Next type of polynomial is irrational and imaginary. So let's take a look actually in a bigger screen here. If we are using the example from the previous notes of plus or minus I times radical 2 as our paired opposite irrational and imaginary roots, if we take our original polynomial and we think about multiplying down and adding, we're going to get I radical 2 written under the 3. We're going to add these 2 values. We get 3 plus I radical 2. And then we still need to do a little multiplication here. This gets a little tricky, so you can see that again I wrote that distribution off to the side here. And I'm multiplying I radical 2 times both the 3 and the other positive I radical 2. So here's the distribution of just 3I radical 2, that first product. And then notice what happens is the 2 radicals become just 2, and then the i's become I squared for the second term of that distribution. I can substitute I squared as negative 1, which means this is actually a real part of my complex number, so I'm going to stick it in the front of the complex part, or of the imaginary part. Negative 2 plus 3I radical 2 is what that simplifies to. So we'll rewrite that underneath there. And I probably would caution you to give a little bit more space when you're doing these special types of synthetic division than you would if these were just integer coefficients, because you can see the work is a little wider here than just one digit, so keep that in mind. But if I add that -2 plus 3i radical 2 to the 2 coefficient that was there before, my 2 and -2 cancel, and I'm just left with the imaginary piece. So I've got another distribution of I radical 2 times 3i radical 2. And if I kind of simplify those pieces, there's my 3. My radicals combine to 2, and I have an I squared, which is just -6. Interestingly enough, with the constant above it, that first one checks out. Remember to check them in opposite pairs, so the first positive root works. Let's see if the negative does as well. We'll pull the 1 down, we'll multiply, and look, we've got a negative I radical 2, which is going to cancel with the positive I radical 2 we had there before. We're left with a 3. And then we have just 3 times I radical 2, so we get -3i radical 2. And we, of course, have that next cancellation happening there that verifies that -I radical 2 is indeed a root that works in this polynomial. And then our last root is, again, translate this. You get x plus 3, set it equal to 0. We know that's our final third choice of just an extra root because we need to get our polynomial up to a degree of 3. So on the last page of this video here, we just have one more type of root to discuss, and that is a complex root. So the two complex roots that we chose for this particular example are 3 plus 2i and 3 minus 2i. This one gets a little bit more involved as far as what the products look like. So you can see again I've provided some space off to the side to show that work. You probably would want to do that in your video as well as you make this project come to fruition, okay? But yeah, leave extra space because we're definitely going to have some more to work with as far as the width of each of these columns. Okay, let's start feeding it through. 3 plus 2i synthetically divided into this polynomial, which we're saying it's a root of to begin with. Pull the 1 down, multiply, and look what happens here with my 2 terms that I get plus the constant or coefficient that was there before. The real parts disappear, basically. I'm just left with the imaginary piece. So now I want to find the product of 3 plus 2i, my root, times this leftover number here, which is 2i. And you can see I've chosen to distribute that here. So I get 6i plus 4i squared. Recall that I squared is -1. We get -4 plus 6i. Over to write that underneath here in our next spot in synthetic. -5 plus -4 gives me -9 plus 6i. Well, using my synthetic algorithm, these two things now, these two complex numbers have to be multiplied. So 3 plus 2i times -9 plus 6i, and our FOIL algorithm gives us these 4 terms. Look what happens in the middle here, you guys. My i's, they cancel out. And what do we know the I squared turns us into? That turns us into a negative. And so I have -27 minus 12, or -39, which coincidentally is what we need to cancel out that very last constant. So we get a 0. Now we know we have complex numbers that appear in conjugate pairs. So if we had 3 plus 2i, the only thing we have to switch, remember, is that sign between the terms. So now it's 3 minus 2i that we want to check out as an extra root. So we're going to do the same process, and you can see here under even more products, I've got more things happening. So this is 3 times 3 minus -2i, because the -2i cancels with the positive 2i that was there. And we're into the next layer here of synthetic. That just becomes +9 minus 6i when I distribute those. And look what happens. Oh my goodness. All of those imaginary parts and all of those real parts end up canceling out. And then again, my final root that I had established was -3, so we'll feed that through synthetically, and we know that all 3 of these roots work. So I hope that helps you guys get started on the process of designing a polynomial that has specific types of roots and what the work would look like for the synthetic work of justifying whether those roots are truly roots or not. Remember, you can do just a few of these types as standalone, or you can do a combination of them. I would caution you every time that you do one of these divisions, please keep in mind that you want to put the pairs through together so that you can kind of see what that ends up giving you later on. Okay? All right. Good luck on your project. Let me know if I can help with anything.